In this video, we are going to talk about the center of mass of an object. So the center of mass as a definition is kind of thought of as the average location of all of the mass of the object. Now, we have to be careful about how we take this average. It is really a weighted average of the object based on the position of the masses that make up the object and their location. We will get more mathematical about what we mean by this quote unquote average location in a moment. The important things from a physics point of view as to why we care about the center of mass is essentially two things. One, the balance point of an object. That is, if I want an object to balance on my finger, say, I need to support the object underneath its center of mass, right? So if I have this pen, the center of mass is quite near the center. But if I have an object with odd weighting like this hammer, here the handle of the hammer has very little mass to it, and the head of the hammer is made of iron and has a lot of mass to it. So if I want to balance the hammer actually balances way over here, which is not near the center of the object. If I wanted to choose the center based on just volume, the center of the hammer is somewhere in here probably, right? If I just want to have as much volume on one side as the other, my center would be somewhere in here. But because the hammer is so much heavier, the head of the hammer is so much heavier than the body, it actually balances over the head of the hammer. So if we can calculate the center of mass, we know where we can balance an object. Okay? Likewise, if we want to talk about gravity on an object, we can think of an object that gravity acts on the center of mass of an object. So if I'm trying to simplify a system, I can think about that gravity is acting on just the center of mass of an object, and I can take a complicated object like this hammer and think of it as a point object at its center of mass. The final nice thing about the center of mass is that it is how objects rotate if they are free of any other forces. So if I just have an object which is, say, undergoing some kind of being thrown in the air, some projectile motion, and it's rotating, it is rotating around its center of mass. You can see this even if I do it for the hammer, right? So if I throw the hammer, you can see how as it rotates, the handle is swinging around and the head of the hammer is not really moving. I'll do it one more time. So the object, the hammer, is rotating around its center of mass here when it is not being influenced by any outside forces like me holding onto it, right? So I can make the hammer rotate around any axis that I want, but if it's not being touched by an outside force, that would be causing a torque. So if it's only under the influence of, say, gravity, the object will rotate around its center of mass. Now let's look more mathematically at how we can calculate the center of mass. So the calculation for the center of mass is really a weighted average of the positions. So you are taking and adding up all of the positions, right? And you are weighting each position by its associated mass. And this counts, so this ... means you just add up all of the masses that you have. So if you have 100 masses, then you have to add up 100 different terms. And then you divide the masses out. So you divide by the total amount of mass of the system, and that gives you your center of mass. A quick note, notice that each term in the top has units of kilograms times meters. And the bottom has units of kilograms, which means that your total units of this are kilograms times meters divided by kilograms is just meters. So the units work out nicely too. Okay, so let's take an example here. Imagine that I have a stick and I have some masses placed along the stick. And the stick itself doesn't have any mass. It's a massless stick that physicists get to make up. Okay, so along this massless stick, I have positioned 3 different masses, and I want to find the center of mass of these masses. So the center of mass here, I'm writing this as a vector because we can do it in 2 dimensions or 3 dimensions, but right now we're only doing it in 1 dimension. So if this is my x equals 0 point, then this would be m1 times 1 meter in the I hat direction, because you have mass 1 here at a distance of 1 meter in the I hat direction. Okay? Plus m2 multiplied by its position, which is 4 meters. So that would be 4 meters I hat plus m3 multiplied by 7 meters, right? Because it's 7 meters away. 7 meters I hat. And I'm going to divide all of this by the total mass. That is 3 plus 5 plus 2 is 10 kilograms. And if you actually do this out, which I will do here, the first term becomes 3 times 1. So it is 3 kilogram meters I hat plus 5 times 4 is 20 kilogram meters I hat plus 2 times 7 is 14 kilogram meters I hat, and I divide it all by the total mass of 10 kilograms, which leads to 17 is 37 is 3.7 meters. Okay, and it is of course in the I hat direction. So my total center of mass is about here. Center of mass. And you can put dots between them to indicate that it's a abbreviation. So my center of mass is right here. Just logically, this seems to make sense, right? I have a very large mass, very close to this, and I have 2 other masses which are on either side, right? It wouldn't make much sense for the center of mass to be over here, right? You can imagine if I had 3 masses arranged like this and I wanted to balance it over here, it just wouldn't work. But you can imagine if I placed, say, some support under this, that it would balance the object. Okay, so this is how center of mass works for a one-dimensional system. You can do it for as many objects as you want. Also, you don't have to choose. Your x equals 0 point actually doesn't matter as long as you choose one point where you say is your origin, and then you always measure from there. Now let's try an example of center of mass where we are working in 2 dimensions instead of just 1. So in 2 dimensions, this equation still holds. It's just that we have x hat or I hat and j hat components, right? We need to keep track of our center of mass both in the x direction and in the y direction. And we can use exactly the same argument that we've used for both projectile motion and 2-dimensional motion and for forces. And that is, if I have a vector equation for position, I can really break that up into its actual components. So this vector, this really represents its position. So I could rewrite it as r instead of x. And this might be helpful in realizing that this contains x and y components. So if I just rewrite my x's here as r's. So if I call this 1, this mass 1 and this mass 2, then this is the vector r2 and this is the vector r1. So relabeling it as r, I didn't change what the vector actually represented. I just wanted to be able to have the x and y components without confusing x as a vector, which contains both x and y components, with x as my x direction, which is the x component. Okay, so each of my vectors has an x component and a y component, right? So I can rewrite my r center of mass as x center of mass I hat plus y center of mass j hat, which must equal m1 times x1 I hat plus y1 j hat, where in my picture, this distance here is my x1 distance, and this distance here is my y1, right? My y component is downward, so it would have a negative y component, and my x position here is positive, so it's going to have a positive component, right? So all I'm doing is writing this r vector in terms of its components, and I can do the exact same thing for my mass 2, which would be x2 I hat plus y2 j hat. Okay, and now we can make exactly the same argument that we've made before, which is that I hat components, motion in the x direction, cannot influence motion in the y direction. Those two perpendicular components cannot influence each other, which means that we can set the center of mass in the x direction equal to just the x components and the center of mass of the y in the y direction equal to just the y components. So that is x center of mass, not a vector, this is a component, equals m1 x1 plus m2 x2 divided by, oh, and this all gets divided by m1 plus m2. And I only have two masses here, but this equation could, just like our original equation, extend to however many masses we have, right? We could have 3, 4, 10 masses. And we can have the y center of mass equal to m1 y1 plus m2 y2, all divided by m1 plus m2. So if we're in 2 dimensions, we just need to apply the exact same formula, right, for however many masses we have in x independently and in y independently. So let's see how that actually works in this case. So I'm going to erase this. So my x center of mass looks like 4 kilograms, that is my mass 1, multiplied by x1, which is 2 meters. Notice I'm not putting vector signs on any of these things because they are just components in the x direction, plus my y2, which looks, or sorry, my x2, so 7 kilograms times 4 meters, and it all gets divided by my total of 11 kilograms. So this looks like 8 plus 7 times 4 is going to be 36 over 11 meters. Likewise, my y center of mass will be the y component of mass 1, which is going to be 4 kilograms multiplied by, negative 1 meters, plus 7 kilograms multiplied by the y component here, which is 4 meters, all divided by, again, 11 kilograms, the total mass. Here I have 4, 28 minus 4 is 24 over 11 meters. So my actual center of mass, 36 over 11 is just over 3. So I go over just over 3, and then I go up. 24 over 11 is just over 2. So my center of mass is over a little more than 3, up a little more than 2, and it is right here. Okay. Good. So notice that it is on a line between the two here. If you only have two masses, then your center of mass will lie on a line between them. If you have more than two masses, that won't be true because they might not all be in a line. I might have a third mass over here, and then it would have to be somewhere in between them. So your center of mass will be in between the two masses somewhere, though, and it's closer to the larger mass, right? It would make sense, just like the center of mass for the hammer was below the head of the hammer, which contained all of the mass. The center of mass here is closer to the 7 kilogram than it is to the 4 kilogram. If I increased the mass of this 4 kilograms, say I made it 20 kilograms instead, our center of mass would shift toward the larger mass. As I increased this lower mass, it would bring the center of mass closer and closer to it. Finally, if we have a solid object that is uniform, that is, it has the same density everywhere, so something like a piece of wood, right? Like a piece of plywood or a piece of paper, something that is a very uniform object, then we can assume that its center of mass is directly at the center of the object. This, of course, would not work for my hammer, right? My hammer is not uniform. Its center of mass is nowhere near the center of the object. It's very close to the heaviest part of the object, right? But this is pretty close to true for my pen, right? Or some other very uniform object. In that case, if you are given an object, you can just assume that that whole object, its center of mass is directly at the center. So for example, if I have a 2 meter by 4 meter sheet of plywood, I can assume that the center of mass is 1 meter over and 2 meters up, right at its center. And then what I could do is say I had 2 sheets of plywood that I put together, and this one's longer, right? And this one is 1 meter high and 6 meters long. Well, then its center of mass is here, which is 3 meters over and 0.5 meters up. So we can treat each of these objects as if it is just a point mass at these two locations, right? So this picture here could turn into this picture here, where if I had, this is my axis, I go over 1 meter here, and I go up 2 meters, and this is mass 1. This dot represents the entire sheet of plywood, right? Because we can assume that all of the mass of the object is concentrated at that point when we're thinking about gravity acting on the object, right? So if we wanted to see how gravity is going to act on these 2 sheets of plywood together, or where the center of mass of these 2 sheets of plywood together is, we can think of these objects not as big kind of square blocks, but we can think of them as individual point masses. So here is the center of mass of this object. It is 1 meter over and 2 meters up, right? Then if I wanted to find the center of mass, and this is poorly drawn, here I would need to be at 3.5, and I am 3 meters over, so 2, 3, my mass 2 would be here. This dot represents this plywood. We are assuming that it acts as if it is a single point at that location. And this is useful when we're thinking about how gravity acts on objects, because we can think of gravity as acting on the center of mass, or if we want to just calculate the center of mass of multiple objects. Remember, this only works if the objects are very uniform in their mass distribution, right? So sheets of plywood, etc., hammers, this doesn't work for.